This is the final and probably the best colloquium of 2008.
No pressure, huh?
So it's a great pleasure to have Yazdani from Princeton here today. After several attempts to get him here, failed on our parts. We have him. He got his PhD at Stanford. In fact, we almost overlapped. He started just after I had finished at Stanford. He was with Aaron Kapitulnik working on metal insulator transitions in two-dimensional films. In fact, the subject of this year's Buckley Prize. And subsequently, he went on to IBM at Almaden and worked with one of the leading people in STM, low-temperature STM, Don Eigler. And that's where he learned a lot of interesting things and showed you can do very interesting physics with STM. He went on to University of Illinois at Urbana and rose up the ranks and then moved to Princeton in 2005 and has been a professor at Princeton in the Department of Physics since. And he does all kinds of beautiful experiments on electrons that live at and near the surface that are correlated and that have interesting electronic structure and interesting interactions. And so today he's going to tell us about a subject that's usually discussed in the context of particle physics, Majorana Fermions and condensed matter.
All right. Thanks very much, Andy. Thanks for having me. Do you know actually how we can dim the front lights?
It's difficult.
It's difficult.
Okay, well, very easy, but it's difficult for Paul.
It's a test of your experimental skills.
Yeah. Let's do
the opposite of what you got.
Let's get in here.
Okay, that's perfect. Oh, no.
It's too dark.
Well, it looks like,
Stop. There's no stop. There's just touch.
Okay, that's fine. That's fine. Oh.
Stop. Let's see.
Well, it looks like it's almost as bad as Princeton in terms of getting the lights right.
It used to be easy. I told you.
Okay, that's good. That's good. Let's just leave it at that. Thank you, Paul.
Stay this way.
Well, it's nice to be here, and I'm going to tell you today about Majorana fermions and condensed matter, but this is a subject that really concerns a new study in condensed matter focused on topological phases. So let me just start by thinking about how we've long known that you can have the same interaction give rise to different phases, and of course in the 20th century we learned about order parameters and how we characterize them, different phases of matter, by broken symmetry using different order parameters. You can read Chaikin and Lubinsky all about that. So in the last, since the quantum Hall physics have been discovered and fractional quantum Hall states, and now in the last 10 years, since the class of new materials called topological insulators and topological metals have been discovered, there's sort of a new focus in condensed matter physics to look at electronic states in which you have no really new order parameter to characterize this phase. They are characterized by, for example, topological properties of the band structure. I will show you some examples of that. But often they possess boundary modes that have exciting physics. For example, they can be Dirac-like electrons, or as I will show you here, Majorana-like excitations in a condensed matter setting. So what I'm going to do today is I'm going to sort of introduce you to the idea of the topological insulator first, just to get you warmed up thinking about these topological phases. And actually kind of a simple example I give in my class to talk about how you can have two different kinds of insulators. And from there, I'm going to go into the topic, which is mainly what I want to speak about today, is how to have a topological superconductor and what does that even mean. And it turns out that the topological superconductor is a way to realize these Majorana edge modes, which are analogous to things people have thinking about in particle physics. And there are experimental proposals there have been theoretical proposals that have been on the table for realizing these superconductors. And there are basically two experiments been done now in the field. One of them done at Delft, some beautiful set of experiments. And as you know, Majorana was a very mysterious physicist that disappeared under mysterious conditions, taking a boat from Palermo, I guess, back to Napoli. And so nobody knows where he is, but we're looking for his particle. So people are desperately looking for his particle in Delft, and we have been desperately looking for his particle in Princeton, and I'm going to tell you about these two experiments. Okay, so let's start nice and easy. Let me remind you about your condensed matter physics, electron band theory. Just think about I have a one-dimensional chain, and in this one-dimensional chain I have two kinds of atoms. And these two kinds of atoms, these two orbitals, as you probably remember, basically gives you two kinds of bands in the band structure of energy versus momentum for electrons moving in this one-dimensional crystal. And if you tune the chemical potential to the right place, you can basically realize an ordinary insulator in this sample. Now, you noted that I have these two hopping matrix elements for electrons hopping inside this unit cell or across the unit cell. So let's imagine those were different. And now ask yourself, where is the electron wave function going to be? So electron wave function in this picture can be in principle anywhere relative to those atoms, depending on how you tune these two parameters. But of course, I haven't respected the symmetry of the situation, like the inversion symmetry relative to the location of the atoms. And if I respected that, I would either have this type of situation, where T1 is greater than T2, you know, that bond is stronger than the other one, or the other way around, T2 greater than T1. So now if you look at these two pictures, they both can give you a band structure where you have an insulator. You have a gap, you can put your chemical potential in the gap, and it would be insulating. There are two bands coming from two types of orbitals per unit cell. This is what we teach our students in courses. Now, but my slide demonstrates something special that is different between these two states. That is, it cuts the edge of the system in such a way that if I made a boundary, you can actually distinguish between these two different insulators. Okay? And what has happened is you have nucleated an edge mode in this system, which comes about if you're in this phase, which is topologically different from the other one because of the parity of the electron wave function. So this is a very simple example.
So the upper one is topologically different than the lower one?
That's right. So in order to get from the one to the other, you have to basically make T2, T2 and T1 have to change places. And basically you have to close this gap and reopen it. And that's the only way you can go from the bottom one to the top one. T1 has to equal T2. So that's an example of what we call a topological phase transition. But if you're just interested in the bulk property of this system, they're both insulating. You couldn't tell them apart. But if you look at the edge, this edge atom has like half a state here, and the energy of that is basically equal to the site energy, which you can set equal to 0 here, which is in the middle of the gap. So this is an example of a one-dimensional system that's topological, but you can imagine that I can extend this to higher dimensions. If I put it on a, let's say, a cylinder, this 1D system, I can make a two-dimensional edge mode associated with a one-dimensional edge mode associated with a two-dimensional solid. So I can extend this idea from 1D to 2D. And if I preserve a time reversal symmetry, there's no magnetic field around, I can't tell whether I have one electron going one way or one electron going the other way. So I basically end up with two edge modes at the edge of this picture. And in the presence of time reversal symmetry, these things basically come in pairs, and Kramer's theorem basically guarantees, for example, spin up and spin down to have a degeneracy at k equals 0. So this is an example how you make a topological insulator in 1D, 2D, and you can have a three-dimensional example.
So in 2D, there's no gap.
So this is the same
You
situation.
showed in the previous one, the 1D case, there was a gap.
So imagine that, imagine I sort of couple these systems together in such a way that I keep the bulk gapped, okay? But I will have a hopping term between those boundary mode that I created for you in the 1D example. And that hopping between that boundary mode will give you a propagating state at the edge of this 2D system. So these things actually have been realized in the laboratory. For example, the first example was mercury telluride, cadmium telluride, which you have an insulating bulk. It's a 2D system. And basically has a two one-dimensional states running around the edge. Spin one running along one way, spin down running around the opposite way. And they also have been realized in 3D samples in which the bulk of the sample is insulating and the surface is conducting. Okay, so this is what a topological insulator is in 2D and 3D. So these are the experiments that actually see the signature of these phases. They are basically boundary experiments. So here's an experiment from Lord Molenkamp in Germany, which uses electrical conductivity to probe the conduction just around the edge of the sample. And when they are in the topological phase, which is tuned with the gate voltage here, tuning the chemical potential into that gap, for example, to have a bulk that is, the chemical potential is in the gap of the bulk, you end up with the 2 quantum of conductance associated with these edge currents running around the sample. Another example is in the 3-dimensional case, my colleague Zahid Hassan and now others have used basically photoemission spectroscopy to actually show that there are these surface electrons living inside the gap of a semiconductor sample, which is this topological insulator, and they have this electronic structure which is Dirac-like, very much like the picture that I showed you before. So where the field is going is to try to now turn to superconductivity. Can you have a topological superconductor? So let me just remind you with superconductivity. Normally we think about BCS superconductors being in a spin singlet state. And we think about the pair of the electrons having a S-like orbital wave function. Okay, this is our ordinary superconductor. So what is a topological superconductor going to look like? Well, we already have a topological superfluid, and that's helium-3. So helium-3, of course, was discovered in the 70s. This is a fermionic cousin of helium-4, and it has 2 superfluid phases, which show up at very, very low temperature, 2 millikelvin or so. And we know that the spin of this fermion, when it makes pairs, it actually makes a spin triplet pairing in a pairing state rather than a spin singlet like we saw in the simple BCS case of an S-wave superconductor. So this is what we call a P-wave superfluid. So why is it P-wave? Well, it's P-wave because the spin part of the wave function is in a triplet state. So if you're going to have the orbital part basically have the right character where you exchange your fermions to have your negative sign for fermions, you will have to have that have a p symmetry to give you a minus sign when you exchange the particles. So this is the first example of what we call a topological superfluid. It's topological because of the fact that these states come in orbital and spin character, and as I will show you in detail, when you have p-wave pairing, you end up with boundary states, which is different than what you would have in the S-wave case. In the S-wave case, you gap the entire Fermi surface, and you just have gapped quasi-particles everywhere. But once you have the p-wave pairing, you end up with having edge states in the material, as I'll show you in the example, in a 1D example in a second.
But not in helium-3. What about?
So in helium-3,
edge states in helium-3.
So in helium-3, you have edge states. You have Andreev states in helium-3, which form actually in the B phase, and they are actually Majorana like quasi-particles. They do indeed form at the boundaries of the system, And people have been looking for these boundary states in helium-3 for a very long time. But the problem is the experiments are very, very difficult because first you have to go to 2 millikelvin to do the experiments. And the other one is that there are no easy ways to get access to the boundary modes of the superfluid experimentally. It's very, very difficult.
Because it's not charged.
Because it's not charged. The other thing you can do is look at the core of vortices created inside helium-3 when you rotate your cryostat. And they should also have exotic modes to the center of vortices. But all of these experiments are very, very difficult to do because they're 2 millikelvin, rotating a giant cryostat, and so on. But the physics of topological superfluidity or superconductivity really goes back to this p-wave pairing business in the 1970s. Now, what we've been looking for are superconducting analogs of helium-3 for a very long time. So we're looking for something that is a spin triplet and a p-wave, like I described. And there are materials in which this type of physics can come about because of strong electronic interaction. So I'll just put the list up here, but these are just things that have been proposed, but there haven't been really sort of smoking gun experiments to suggest that they are really topological superconductors.
The thinking is that the 5/2 state could be.
Could be. So it turns out the natural explanation, the natural wave function you would write for the 5/2 state, which was proposed by Moore and Reed, is basically a BCS-like wave function, like a p-wave one that I don't remember whether it's Anderson or Morale or the other one. It's a similar kind of wave function. It's a natural p-wave superfluid. The other one is strontium ruthenate, which is magnetic and superconducting, and there is a lot of controversy as to whether it's a p-wave superconductor. So the field actually got revived, or in retrospect, it got revived by a very simple paper, which is less than 2 pages long, written by Kitaev, where he basically considered a very, very simple model. And people got much more motivated to look for topological superconductivity because of this paper. So let me go through the idea here. Imagine you have sites, and let's just think that our fermions are spinless, okay? And I'll tell you how we get spinless fermions in a second. And just imagine you have hopping between these different sites, and you have also pairing. Has pairing happening on nearest neighbor sites. It has to be so. It has to be not on site, S-wave-like, because otherwise here you have spinless fermions. So since you've taken spin out of the problem, whatever pairing you would write will have to be sort of odd on their, say, momentum switching-like character, or it would be nearest neighbor site. Is the simplest thing you can write. This is a very simple model. In fact, I assigned this model and this paper as a final exam problem in my class with a few hints for people to see that it actually has a lot of interesting physics, very much related to that 1D model I showed you at the beginning. So what Kitaev did was he said, okay, let's take these fermionic operators, which are basically complex operators, and write them in terms of 2 real operators. So this is fermions are complex entities. You write them in terms of just their real and imaginary part. So this is what we do in superconductivity anyway, most of the time, when we write the Bogoliubov transformation for diagonalizing the BCS Hamiltonian. And what he found was that basically if you go through this simple model and do this decomposition of the fermions into these what we now call Majorana operators, you find that this Hamiltonian actually has 2 phases, very much similar to the first picture I showed you in terms of a topological insulator, where you can pair up your fermions from the Majorana operators using basically either Majoranas from the same site or Majoranas from nearest neighbor sites. So this simple picture is very analogous to the first model that I showed you. It's basically the easiest example of a topological superconductor you could have. You have pairing. Pairing is between nearest neighbor sites. And the pairing is there in both models, but in one case you have half an electron living on this end, or half of a hole living on this end, and the other half is living on the other end. Okay, so this is a very interesting beast. So first of all, it is a Majorana. It's a real, we just took electrons operator, which is complex, and wrote it in terms of a real fermion. So it's its own antiparticle. And here, basically, within the context of why does this show up in condensed matter physics, and why does it have connection to superconductivity, you can see that in superconductivity, you mix electrons and holes naturally by the pairing interaction. So it's very natural that this type of model would allow you to create an equal mixture of electron and hole, which would be the Majorana. So the goal has been to try to realize this model experimentally. And I'm going to show you two experiments that claim to do this, one by our group. But let me just also mention that in high energy physics and cosmology, of course, people are looking for Majorana fermions. And this is actually a field that has a lot of different experiments in it. And here's a list of them. The top candidate, of course, is neutrinos, and whether neutrinos are Majorana fermions. But these are free particles, of course. And there's a large list of experiments, most notably those looking for a neutrino-less double beta decay, in which a neutrino and antineutrino, basically two neutrinos annihilate one another if they were indeed Majorana fermions. This observation will at least tell you that neutrinos are perhaps Majorana fermions. So coming back to our problem, the thing that's different about the Majorana in our picture is that it's this non-local object. It comes in pairs. So you have you started with fermions. So you split the fermion apart, but you do it in a non-local way. The whole bulk of the system is gapped. And in here, you have ended up with basically taking that electron and splitting it on either end of the system. This quasi-particle state can be occupied or unoccupied, but if you make it very, very long, infinitely long, this end is not talking to the other end through the superconductor. So if you want it to change its quantum state, you have to operate at the two ends of the wire at the same time. So this is the basis of why, one of the bases on which people are excited about this idea is that this gives you a way to write quantum information in a non-local fashion. So this is the advantage of, if you like, bound fermions, Majorana fermions in a condensed matter setting. It allows you to create this non-local object, which may become a topological qubit. And also it has non-abelian statistics, which means that if you take one around the other, there are 2D models in which you have Majoranas. And in 1D you can make different type of structures, as I will show you later in the talk, when you take one around the other and so on, you can create basically braiding, in which you get very non-trivial phases. If you take one Majorana around the other, you get a different answer if you do it the other way around. Okay. All right. So how do we is there a way to make a Kitaev chain? So this is where our field has been focused on. So what are the ingredients? The ingredients is basically make spinless fermions. So how do we make spinless fermions? Well, remember the first part of this talk where I told you how we get a topological insulator. And on its surface, you have these electrons which are basically bound to live on top of it. Their band structure looks like this Dirac band structure. They are protected by time reversal symmetry. They come basically, they come in this, according to Kramer's theorem. And basically, you have a situation on the surface of these topological superconductors in which the electrons' momentum are spin and momentum are locked together. So this is their band structure. So if you like, spin and momentum are locked together. So you can think of this as a spinless electron. Because now if I take this, and as Fu and Kane basically propose, and couple it to an ordinary BCS superconductor via what's called the proximity effect, I can basically introduce pairing onto the surface of a topological insulator, and this pairing would have to be P wave, okay? Because spin is no longer in the problem. So this was the first idea to try to realize Kitaev's chain. You make a sort of a 1D structure of this. In this case, actually, you take a 2D surface state, and that's the proposal was you fabricate structures in which you will have Majorana actually in vortices, or you have at the edges of the system. So people took this idea and actually made it simpler. They said, what are the ingredients? We want spin to be out of the problem. So imagine I have a wire, so a nanowire made out of a semiconductor. And this nanowire basically has a band structure which is like a parabola. But imagine this nanowire has strong spin-orbit coupling. Okay, the electrons spin and momentum are locked together, or they're made out of heavy elements. So what that does is it takes the parabola that you're familiar with, it basically splits it into these blue and red parabola. Okay, spin-orbit coupling does that. Now imagine I apply a parallel magnetic field. Okay. And it's parallel to the wire. And if I do that, basically, it opens up a gap at k equals 0. This is just a Zeeman splitting. So now the band structure of this wire is the black line. And over here, I have spin up, and over here, I have spin down. Basically, it's very analogous to that structure that Fu and Kane started with. But now I have a one-dimensional system. Now, you put this nanowire on top of a superconductor, you should have P wave pairing. Okay? So let me just go through that. Here, the band structure gives you this spin structure where this is spin up and spin down. These spins are dictated by spin-orbit interaction. They're out of the problem. Okay? Spin is no longer a good quantum number. Okay? But if you introduce pairing, then it has to be basically, when you flip k, the orbital part has to be antisymmetric.
Semiconductor, but the way you drawn it, it looks like a metal.
No, this is supposed. I'll show you. So this was proposed to use with like semiconductor with strong spin-orbit coupling. The experiment I'll show you was done on indium and timonite.
Okay, it's the field that makes it a semiconductor here. Do you split? Do you put a gap?
Oh, I see what you're saying.
Yeah, but the way you've drawn the Fermi level.
Yeah. Think about this as the shells of the system, and I can basically put the chemical potential into the conduction or the valence band. Yes. It doesn't have to be a semiconductor. That's the band structure you need. You're correct. So this experiment was proposed theoretically, and colleagues at Delft have been looking for Majoranas in Delft. This is for a long time. This is a nice picture. They do beautiful things in Delft. So here's the experimenters did exactly what the theorists proposed. You take a superconductor, you put a nanowire which has strong spin-orbit coupling, and then you have an electrode here. So this part of the wire is superconducting. This part of the wire is not superconducting because it's not in contact. Here they have a bunch of gates which you can't see. They can deplete the electrons out of this region of the wire to make a tunnel junction, to pass a current between the normal metal through a tunnel junction into the superconductor. So normally when something goes superconducting, it opens up a gap, right? Superconducting gap. And you should just see a gap. Now, what they did is they ramped the magnetic field. So here's at zero field, you see a gap. This is the induced gap in this superconducting wire. The gap is not very hard, it doesn't go to zero, but as they increase the magnetic field, they notice that there is a peak, there is a zero bias peak rising, and then it goes away along with everything else as they go to a large field. Okay? So what you have here is a zero bias peak inside a superconductor. So remember, here you have electron-like excitation. here on the positive side, whole light excitation on the negative side. So having a peak right at 0, you just have exactly the equal mixture, which is what the theory would have predicted for being a Majorana fermion. So then comes the questions. Is the zero bias peak really coming from the end of the wire? Right? This is a transport experiment. You're passing a current through this whole structure. So that's one problem with this experiment, or one potential problem. The other problem is that you apply a magnetic field to create the right condition to have the Majorana show up. And when you do that, as we know, as we see in this picture, you suppress superconductivity. Okay? So if you suppress superconductivity, and if the end of the wire, the superconductivity is weak, maybe you end up with a little normal region. And if you have a normal region, you have maybe like a quantum dot in this normal region. So you can end up having a zero bias peak due to something completely different, called the Kondo effect. So Kondo effect happens in metals with magnetic impurity, but it also happens in quantum dots, where you have an odd number of electrons. So this zero bias peak here is a many-body interaction that shows up because you're doing a spin flip scattering from this spin that's basically living inside this quantum dot. Okay? This is due to very different physics than a Majorana. Okay? And this shows up only when you get normal electrons. If you have superconducting electrons, it should go away. So there's been kind of a debate in the community. These experiments have been beautifully reproduced, is whether this is really the smoking gun. So this is where we got interested in this story. So okay, you know, Princeton is not quite as charming as Delft, and it is in New Jersey. And so we've been looking for Majoranas in Princeton. So this is the team that have done all the work. So actually I'm going to talk about the rest of the talk. This work has been driven by Stefan, my postdoc, who's actually now at Delft, on his way to Caltech, a graduate student Ilya. This is and Sungjun, another postdoc, and this is a new crew joining the project. And the key guy here I've talked a lot with, and the ideas came from, is Andrej Brnovic, the theorist in our department, and his group, and also working very closely with Alan MacDonald. So we had a very different idea. We thought, what if you try to create pairing using a chain of magnetic atoms? So our original idea was that, look, if you have magnetic atoms and somehow they make some sort of a modulated magnetic texture, and you put it on this superconductor, doesn't this kind of look like spin-orbit coupling? Okay. And so this started as a theoretical project, and we took this model, and we started thinking about it, and we thought, oh, you know, it does actually make sense. If you have magnetism on a given site, it forces basically electrons to have the same spin, so spin singlet pairing on that site is no good, is not going to happen. But if I get two sites where their spins are sort of canted relative to one another, for whatever reason, okay, just give me that, then I can take a pair from my host superconductor and sort of pop it into the nearest neighbor site. And now if these are canted rather than being perfectly antiferromagnetic, they can actually, pairs can hop along this chain. So this is kind of the plumber level understanding you can have of this system.
So I don't understand, what's the difference between that picture and that picture?
So I'm just focusing on two sites which have different spin. It's just saying that they're not aligned this way or anti-aligned. And just think about having a Cooper pair from the host superconductor hop on and hop off this site. If these two spins were not perfectly aligned, then you would have some probability to put a Cooper pair on nearest neighbor sites. And that's basically my P-wave pairing. Okay? And you already can see that spin is out of the problem because spin on this chain is well defined because of the magnetism. Okay? But actually, a lot of theoretical calculation goes behind that, and I won't bore you with the details. You can actually solve what this problem does using basically Bogoliubov-de Gennes. This is basically the gap of your superconducting host, and this is the strength of the magnetism on these given sites. And in this calculation, we just assume that there was a spin spiral. And basically what happens is that as you crank up the local magnetism on a given site, you basically close the superconducting gap, which would be forming on this chain at some critical value of the local magnetic field. And once you go beyond that, it opens up again, and right where you are in this phase, one of the excitation spectrums remain at 0, and basically this is the Majorana mode that's forming if you have a strong enough magnet, and basically you have in this model a modulatory magnetic structure. So this is what the theory shows us.
What controls B?
Well, in our case, is what atom you pick to put on top of this surface. Okay, so that's what I'm going to show you in the experiment. So the theory basically shows that if you do a calculation and ask about the Majorana wave function spatially, it would actually be stuck at the end of the chain. Now, this is actually a 2D calculation. But
what's Y?
what's Y? Y is perpendicular. So this is a 2D calculation. So this is along the chain. This is sort of into the picture, into the board. And this is basically showing you that you have the 0 energy state, right? The first energy state is at 0. It's sort of tied to the end of the wire, and it has these modulations associated with the Fermi wavelength in the system. Then we realized we actually don't need this fancy spin spiral after all, if you actually have a superconductor that has strong spin-orbital interaction in its bulk. Okay? So the same physics comes about if you basically have a ferromagnetic chain, which is much easier to realize experimentally. Most things would like to make ferromagnetic alignment. And you have a strong spin-orbit coupling, which basically gives you an effective spiral-like arrangement for the electrons as they hop along. There is another interaction that comes into this problem. This basically showed the same kind of physics in the theoretical calculations. All right. So there are these two limits of this theoretical problem. This is kind of a generic thing that should happen. You have spin spiral, you have spin texture. If you use spin-orbit coupling, as soon as you have any kind of misalignment of the spins, you have some component of p-wave pairing, and we would expect to see a Majorana, a zero bias peak, at the end of the chain. So that's the idea. So how do we do the experiment? Well, this system also lends itself to not only sort of generically simple things, magnets, superconductors, simple superconductors, but also it lends itself to STM experiments. So STM, let me just remind you, you can do your typical imaging where you just measure a constant current maps, constant tunneling current between the tip and the sample. That gives you the topography. You can also do local spectroscopy. You can park your tip at some location, measure the tunneling rate. Is it tunneling spectra, tunneling rate as a function of the voltage between the tip and the sample? So if you have, let's say, a semiconductor, or you have a gap. But you can map that information as a function of space. Okay? And this is what we do for a living. This is what my lab does. We basically make these movies of what electrons do as a function of energy. And we basically use it to study all kinds of problems, from topological states to spins on superconductors to high TC. It's a very useful technique. And let me just skip through these next two slides and just bring it back to. So we've done these experiments on many kinds of systems. This is what we do. Okay, so how do we make this arrangement? Ferromagnet with a superconductor with strong spin-orbit coupling. So the way we do these experiments is actually done in a new instrument in our lab, which is quite sophisticated. It's a low-temperature STM, operates at 1.4 Kelvin, and this is sort of the tail end of the cryostat. And inside there is where the STM is, but you can actually move the STM into this chamber, and you can prepare samples in this other chamber and basically move everything in situ inside ultra-high vacuum. You can evaporate things on top of the sample, clean samples, and this is a microscope that allows us to do all that. And as I will show you, it actually allows us to also do spin polarized STM experiments to actually measure the magnetic properties of these chains. Okay, so we started doing experiments on lead. Lead is a good choice. It's probably one of the heaviest things around that superconducts. So this is a surface of lead 110. It's been sputtered and annealed to create very flat surfaces. This is basically an atomically smooth surface. It's a 110 surface, so it has these sort of grooves associated with this chain of atoms, atomically ordered, and then you have steps, single atom steps. These are atomic terraces in between the two. Now, before we do anything, this is just probe superconductivity. This is a beautiful BCS superconductor. You can measure its tunneling gap. It just has a nice gap. And you can do very high resolution experiments in this machine. You can even see signatures of photon mediating the pairing interaction right on top of the tunneling spectrum. And as I mentioned, lead is good, has strong spin-orbit interaction, which gives us this canting between electron spin as it moves through lead. So this is how we made our wire. And the reason we chose lead 110 is because it has this anisotropic surface structure, okay, which you saw in those zoomed in atomic images. So the way we make the wire is we take lead after it's been cleaned and we evaporate some iron right on top of it. And at the beginning you sort of see that there are these ugly looking blobs, okay? But you notice that there are these lines coming out of the blobs. And basically these chains are forming because of the anisotropic structure of the substrate. And if you zoom in, you can find chains that can be relatively long. Okay, they're not perfect yet, but they can be 200 or 400 or 500 long overall, but they can have regions that are 200-300 angstroms that are very, very clean. And if you zoom in on these chains, you can see that there are single atom wide chains. So underlying here is the structure of the lead substrate. You can see the lead crystal, and this basically line has a center between two grooves. And essentially what you're doing here is you're imaging your tip with this structure. All right, so is it magnetic? Well, this took us a long time to figure out. So you have to do an in situ experiment to measure the magnetism of this atomic chain. And the way we do this is you use a tip that's coated with magnetic atom, and this very much works like the disk drive heads that I guess used to be, where you basically measuring the conductance between the tip and the sample, and if they're both magnetic, if their spins are aligned, you get high conductance. If their spins are anti-aligned, you get low conductance. So that's great, but what we also have is in this instrument is we have the ability to sweep an external magnetic field, which allows us to kind of dial in the spin of the tip, the magnetization of the tip, which changes basically the spin direction of the electrons coming out of the tip. Or you can switch the magnetization of the tip or the sample. So this is what happens when you tunnel onto these chains. So this is measuring the tunneling rate between the tip and the sample as a function of magnetic field perpendicular to the sample. Okay? So if you were just tunneling between normal metal and you were at low fields, it shouldn't matter whether you're applying a small field. But here you have a situation where you have two ferromagnets, or we believe. It's a two ferromagnet situation, because as you sweep the field, you get switching effects, but you also have a low or high conductance state, indicative of basically aligned or anti-aligned situation between the tip and the sample. So this basically shows that we have tunneling between two ferromagnets. Tip is ferromagnetic, also the wire is ferromagnetic. Another question is which one is switching, and in the process of figuring that out, we discovered something very unusual, which turned out to be very important. If we put the tip not on the chain, but far away on the lead substrate, lead is not magnetic, you would think that tunneling between a magnetic tip and a non-magnetic sample wouldn't care which direction you magnetize your tip, right? But we found that if you sweep the field perpendicular to the substrate, these green points have been measured on the substrate, the tunneling is suppressed. And this suppression basically tells you as I take the tip's magnetization and pull it out of the sample or into the sample, away from the sample surface, I get a low conductance. So the spins in the sample like to be parallel to the surface. So this is a signature of spin-orbit coupling in this experiment, which is very, very nice, because it's the first time, at least in the STM setup, where you can just take a magnetized tip and actually probe spin-orbit interaction in which you don't have any preferred spin direction, but you have a spin anisotropy, at least in this case, at the surface.
This is the spin orbit of the lead.
At the surface of the lead.
At the surface.
This is measured far away. So you see, the
Far away from the magnetic.
yes, far away from it. So you notice that this tunneling is symmetric in field, so there is no ferromagnetism is involved. You see some switching effect, which is actually switching of my tip, but that's exactly right.
And this effect is smaller than the tunneling magnetoresistance you see in the red curve.
It's not that, it is smaller, so it's like, yeah, you're right. So it's 0.15 to 0.2, and here it depends on the tip.
Okay.
Depends on the tip. It's not small. Spin-orbit coupling in lead, it can be large. Depends on the tip. So if you divide those two signals, you can basically measure the hysteresis loop of your tip, okay, which is not very interesting, but it's important to have. So this is the switching happens when I switch the tip. Actually, the wire does not switch, and we have some theory for that, which I will not dwell on. Okay, so we have, let me go forward. So I explained all this. So we have the ingredients. We have a ferromagnetic chain. We have a superconductor which has strong spin orbit. We can actually see the effect of spin orbit in the experiment. So let's look for Majorana. So here's my wire, and red is a location at which I can measure the tunneling density of state. So when I'm on the lead, just a few angstroms away from this wire, I see a nice superconducting gap of lead. That's what that is. It's just gapped, okay? And what you find as you move in, and this is what this movie shows, is a lot of things are happening. You saw that there is a lot of things happen at zero bias. I'll show you that again. So when you move onto the wire, okay, this wire is ferromagnetic. Doesn't like superconductivity that much. But I guess it likes it enough at 1.4 Kelvin to show suppression. So there is an incomplete pairing at this temperature, but there is a suppression of density of states indicative of a proximatized pairing onto this wire. So let me just show you, this is the same plot, and here's what the spectra looks like if you put the tip not exactly at the end, but close to the end within about 10 angstroms. You see a very clear zero bias peak. Now you notice that this curve, when I'm tunneling into the iron, or even when I'm at the end, when I see the zero bias peak, has this anisotropic peak structure. This is very typical of things we see when we tunnel into magnetic impurities on a superconductor. The reason is they introduce states inside the gap, not necessarily at zero, and tunneling in and tunneling out could be different because they have a potential is whether attractive or repulsive to electrons. That's a bit of a detail. But the exciting thing is this zero bias peak, which is happening near this end of this wire. So here's another wire. This is now measuring the zero bias peak at two ends of the same wire. Here's on this end, here's on that end. You see the zero bias peak in the middle. They look very similar. And you can run the movie as you come in on both ends. It looks rather similar. There are fluctuations in the background. And if you go to this blob in the middle, you also see enhanced zero bias peaks. But when we get to it, the structure of the wire is not very clear, so we don't quite know what to make of it at this point. Okay, we like to make perfectly clean wires, and we haven't accomplished that yet. Okay. So the power of the STM is that you can not only just take those spectra, but you can actually make a map. You can take a picture of what electrons are doing at each energy. So these are energies that are inside the lead's gap. So that's why the background here, for example, blue is low. This is outside the lead's gap, and red on the wire. Okay, so these are the states that are away from zero on the wire. You can see that it has modulations associated with probably structural modulation, which I won't dwell on, as well as what the electron wavelengths are doing. So here's the exciting thing. You actually see a zero bias peak, which is tied to the very end of the wire. Okay? And this is very reproducible We have now more than 50, 60 wires, which basically show this behavior. Okay, how about some checks? So is it reproducible? Yes. There are some chains that don't show this zero bias peak. We don't quite know yet, but we know from theory that the structure is quite sensitive, and I won't go into the details of that, but the structure can change whether you're in the topological phase or not. Is the magnetism somehow different at the end of the wire or not? Well, we don't think so. If anything, the magnetism at the end of the wire is weaker, okay? So there doesn't look like there is a lot changing at the end of the wire magnetically to sort of say that this is a very different kind of situation at the end of the wire. But most importantly is the question is whether this is really tied to superconductivity. So remember the Delft experiment, you apply the magnetic field to create the right band structure. Here we don't apply the magnetic field. Okay, we have the magnetic field from the magnet, which is an advantage. The reason it's an advantage because we don't have to apply the field everywhere. They have to apply the field everywhere, including in the superconductor that's supporting their nanowire. So if you apply a magnetic field to the superconductor, you can weaken it. All right? Here, what we can do is we can ask the question, let's drive this superconductor normal, and if this peak was due to this Kondo effect, it should only get bigger because it's just a screening effect. You have more electrons near the Fermi energy. It's just going to screen the magnetic impurity. So here's a wire that was measured at just basically showing us the zero bias peak. And here's the same wire measured just at 100 millitesla, where the lead has gone normal. I'm sorry, this is a very boring movie, but basically you see nothing. Okay. So in the normal state, once I take the lead and make it normal, there is nothing special about the excitation spectrum at the end of the wire. You induce superconductivity, and as soon as you do that, you create this zero bias peak at the end. Okay, so this is bringing me, so this is not the Kondo effect. So I may even end it, yes. So what we are excited about is that this is a new platform for basically engineering a P-wave superconductor. So we've been looking for P-wave superconductivity for a long time in exotic materials. And our strategy has been look for strong electronic correlations that basically, like helium-3, gives you P-wave pairing state as the most stable kind of the ground state of paired states. Here, we're cheating. We're using BCS superconductor, phonon-mediated superconductivity, which is not exotic, but we are creating an exotic situation by using magnetism. The magnetism here being ferromagnetism plus spin-orbit coupling. You need spin-orbit coupling, otherwise you're not going to pair in this situation because it's ferromagnetic. So this is why this is an interesting platform. And it has several different extensions, which I'll show you in a minute. So we are very excited because we think that the signature is very strong. So what is the future? What are we doing next? Well, I showed you these zero bias peaks. You saw that they have some energy width, which have to do with the temperature at which this experiment has been done. Now, if the Majoranas are inside this wire, they can talk to each other through the wire. And if they talk to each other, they will split, and they will no longer be at zero energy. So the name of the game in this business is how zero is your zero? Is it really zero, or is it split and you just can't see it? So we are extending these experiments to millikelvins. This is an instrument that gets down to 20 millikelvin, and they just had their first successful run of making these first magnetic chains. And the other thing we are trying to do is optimize the system. It turns out basically how strong is superconductivity on this chain depends on basically two parameters. Well, three parameters. First of all, how strong is your superconductivity in your host? Well, we use lead. It has a very large gap. It's hard to do better unless you use high TC, but high TC is a D-wave superconductor, so that's a different business. But what you want to do is optimize the other two parameters. Well, spin-orbit coupling, we can't really optimize further because lead is basically as strong as a spin-orbit coupling as it comes. But what you can do is make the magnetism on the wire weaker. So if you make it a little bit weaker, but it's magnetic still, you might be able to make this even more robust. And basically make the temperature at which there is an associated P wave gap on this wire, which is right now, we believe, very small. You can make that gap bigger if you make the magnetism weaker. So of course, we all want to do the next big thing, which is to braid them. Okay? Which is to move the Majoranas around one another. So we got some crazy ideas. The crazy ideas come from thinking about, let's not make a wire, let's make a ring. So if you could make a ring, then it doesn't have any ends, right? So you can be in the topological phase, but it has no Majoranas for you to look at, okay? Because it has no edge. Now, in our system, if you apply a weak magnetic field, if you could make your superconductors survive in a weak magnetic field, this magnetic field can basically act like a tuning parameter, which the angle of it relative to your wire can be used to turn part of the wire topological and part of it non-topological. It turns out, basically, it depends on the angle. Okay, we have done a theory calculation here. So you have, actually, this should be reversed. This is a topological, oh, actually, maybe not. This is topologically, let's say, trivial. This region, when the wire is perpendicular to the magnetic field, has gone parallel, it's gone trivial, and this part remains topological. So you dynamically create an edge. And you have basically, and Majoranas come in pairs. As soon as you have a region which is topological, at the two ends you have Majoranas. And if you rotate the field, you will move them. So this is kind of the pie in the sky experiment. If you use a thin film superconductor, you apply a parallel field, it doesn't disturb superconductivity in our thin film. And if you can make a ring on its surface, if you stabilize the topological phase, then if you apply a parallel field, you can dynamically create them. And then my theorist colleagues went a little nuts, and they started thinking about like the Olympic Games. Well, what can you do if you have multiple rings, interpenetrating rings? And what you can do there is you can braid them. So basically, if you make multiple rings, as you rotate the magnetic field, and this is completely crazy, but I'll be happy with just seeing this dynamical edge. But then you can have a situation where the one pair of Majorana, one member of one pair can be rotated around another pair. And basically, they tell me that this is how they can realize a lot of different quantum-like entanglement operations. Okay, so I'm out of time, and let me just add that this optimization, like I mentioned, is one direction we are pushing. The other one, which is kind of equally exciting, is get out of 1D, go to 2D. So here you have a 2D, what we call a P plus IP superconductor, where you will have a chiral edge mode running around the edge of it. It's magnetic this way, and it will have electrons basically in this Majorana mode running around the edge. So with that, let me just put the picture of everybody working on this project. I was told to end promptly at 5 because of the Christmas party, but I went a few minutes over. So thank you.
Thank you very much. Yeah.
So I'm a little still confused about the mode. If it's one dimensional, the edge is a point.
Yeah.
But isn't the mode still going around the wire this way? What is it, a mode at a point? Isn't it still going, I mean, it's a wire, isn't it going around?
So you can ask, so the wave function of the Majorana will have whatever orbital symmetry you will put in this, you know, you start with a wire, and you have d orbitals, and you have the azimuthal symmetry, and then you can ask, you know, I form this Majorana at the end, what's the wave function look like, what's the orbital content, and this is correct. There are these questions you can ask.
It can't be really a point.
Oh, wait, okay. First of all, the wave function is not, it actually decays on a length scale, which is associated with several things.
No, I'm not talking about in the direction of the wire. I'm talking about transverse to the wire. There has to be some kind
Yeah,
of...
sure. It has a symmetry of the original orbitals that you started with.
Right, so it's not really physically one-dimensional. There are physical degrees of freedom transverse to the wire. Right?
Yes.
And that's what the mode is. I mean, it's a mode. It's a physical.
Well, what I mean by mode is if you look at energy space, there is a single state at zero energy. And what you're asking about is what does it look like in terms of its orbital wave function? But it's a single state.
Right.
Any questions?
I guess it's not easy to make long chains in the system. And one of the things you want to try is to get the two ends to interact. You try to sample short wire?
Yeah, so if you look at our paper in the supplement, we have some short stubby wires, which basically you have a mound, some little short thing come out of it, and you did the study of it. And in fact, there we see that the zero bias peak is suppressed.
So not split, but suppressed. It doesn't get split.
Well, yeah, the experiments don't have a good enough resolution. So the spatial structure, when we do see the zero bias peak very clearly, is about 15 angstroms. Okay? The wires we've seen are that where we see a change in the zero bias peak are about 30 or 40 angstroms. We see a suppression. But yeah, I think basically we would like to do very clean experiments to answer the kind of question you're asking is, can you see them shorter wire and watch it basically go and split? I mean, that's what you want to do. So not just shorter wire, longer wires.
So on this two-dimensional thing, if you have a point, then it has the right codimensions, so when you move it around, you can create this winding. But then how in 3 dimensions did you actually braid these, could you theoretically braid these things together? Because you have one extra dimension, so I don't really understand how it's like...
Oh, the braiding thing that I showed? Oh, okay, so I can show you that. I mean, basically, yeah, look at this picture. So these are all in plane rings, Majoranas at the green dot, at the points, and the field is being rotated, and it shows the step by which you can basically take one around the other, and
All these rings are engaged.
all flat, but interpenetrating.
So they touch.
They touch, they overlap. Yeah, I mean, this is an idea. I don't know whether this would work. The details of these points could be complicated, but not necessarily. I think they devise these things to really make sure you're moving things through regions where, like here, this is, I believe, trivial. This is topological, and as you rotate from here to there, you can basically advance one versus the other. So the idea here is all in plane. And if nothing funny happens at these points, which you could, then you can imagine moving one member around the other. Moving around is not the right word. Exchange is perhaps the right word.
Have you thought about what would happen if something like the domain wall formed in your wire?
Oh,
Where you
yeah.
have then a
So
change in the magnetic order.
so if you had the domain wall like this will nucleate 2 Majoranas because they always come in pairs. So this will give you a signature. So you could look for that. Absolutely.
That's interesting.
Yeah. So this the thing that's kind of neat about this is if you can get a handle on magnetism and create different textures, you can ask very interesting questions about things that are basically people have thought about, like in helium-3, about different kind of complex boundaries. And here you're basically manipulating things with magnetism, if it can work.
Any questions? Everyone ready to go to the holiday party, I guess? Let's thank Ali again.